A shocking story. Charge. Electric charge. The positives and negatives revealed. Finally, the world will know. Oh, I'm sorry. Okay, here we go. Important concepts that I've already stressed before, but I'm going to stress them again and again because they are important. Electrons and protons have the exact same size charge, except, of course, that electrons are negative and protons are positive. But this one is even more important. Opposite charges attract, and like charges repel. If you keep that in mind, you're going to do just fine. Here's a situation where you have a comb, as shown there to the left, which is electrically neutral, which means there are the same number of protons and electrons in that comb. And you have some little bits of paper represented by those shapes. And those are also electrically neutral. If you comb your hair, the comb would remove electrons from your hair and become negatively charged. Then, if you brought the comb close to those pieces of paper, it would actually attract them. But those pieces of paper are still neutral. So how does this happen? Because it seems as though negative charges should attract positives, but should they attract neutral things? Well, it turns out, yes, there is a mechanism for this. And the answer is polarization. This is not like the polarization that we studied in waves. The excess electrons on the comb repel electrons in the paper. Remember, opposite charges attract, like charges repel. So some of those electrons in the paper move away from the comb. And this leaves the top of the paper looking positive. And those positive charges are then attracted to the negative charged comb, and the paper jumps onto the comb. Notice the little piece of paper? There are positive charges on the top because the negatives have been repelled by the negatives in the comb, and so they move away. Now, paper is not a good conductor, but the repulsive force between the electrons is strong enough to make them move away slightly, leaving the top of the paper looking positive. And positives are attracted to negatives, so the paper moves up. But the paper is still neutral. It still has the same number of electrons as protons. The charges have been polarized. I don't know if you've seen this trick where someone rubs a balloon on a sweater and then sticks the balloon to a wall. This happens because, again, there's polarization. And let's take a look at the situation. And here's the first situation where the negatively charged balloon is far from the wall, and the wall is neutral. And what's going to happen is, if we look at the way those charges are distributed in the wall, it's all random. And they're oriented in all different directions. But then, as we bring the negatively charged balloon into the wall, take a moment, think of what would happen. And the answer is the following. the negative charges on the balloon repel some of the negative charges in the wall, and they move away, leaving that side of the wall near the balloon looking positive, but just that small portion of the wall. So here's what it looks like. If you look, the negative charges on the balloon have repelled some of the negative charges in the wall, and so the surface of the wall looks positive, and so negatives are attracted to positives. So the balloon sticks. But if you look at the rest of the charges in the wall is still neutral, and everywhere except where the balloon is, all of those charges are randomly oriented. And so we don't really change the charge of the wall, we just polarize a small bit of it. Now, the basics of charge. The variable name we're going to use is Q, or capital Q. And the unit for charge is the coulomb, which is named after a French engineer and scientist who did a lot of work on electricity. And it's abbreviated capital C for Coulomb. And if you had 1 Coulomb of charge, you would have 6.25 times 10 to the 18 electrons. But because protons have the same magnitude of charge as electrons, you could also have 6.25 times 10 to the 18 protons. This conversion number is on the equation sheet, so you don't have to memorize it. But this one is very much more important, and you don't have to memorize it, but you're probably going to use it so often that you'll know it. The charge on an electron, 1 electron, is negative 1.6 times 10 to the negative 19 Coulomb. Every electron in the universe has that exact charge. And similarly, for a proton, Q sub p, the charge would be positive 1.6 times 10 to the negative 19 Coulomb. Every proton in the universe has that charge. Sometimes calculations are made easier if we take that charge, 1.6 times 10 to the negative 19 Coulomb, and just call it 1 elementary charge. We're going to find out very shortly that you can't have less than that charge. And so we can boil it down and say if something has 1.6 times 10 to the negative 19 Coulomb charge, then we can say that's 1 elementary charge. And that can sometimes make our calculations a lot simpler. Here's some examples. If you had 10 electrons, what would their net charge be in coulombs? And the answer is negative 1.6 times 10 to the negative 18 Coulomb. If you measured a net charge of 9.6 times 10 to the negative 19 Coulomb, how many elementary charges would there be? And the answer is 6 elementary charges. You would simply divide that 9.6 times 10 to the negative 19 Coulomb by 1.6 times 10 to the negative 19 Coulomb, and you get 6 elementary charges. And what type of particle would make up the net charge that we found in question number 2? And the answer is there would be 6 protons, because the charge is positive.